Okay, so we're going to do some practice runs. So get out your pencil and paper, and we're going to, and your packets, your information, your lecture materials, whatever the case may be, wherever you've stored this stuff down. And I'm going to give you some scenarios, and we're going to see how well you apply geotolerance to the application. So we're going to keep the parts pretty simple. This will rely on your ability to go and look at the chart to find out what type you should use and how to correctly use it. So we're going to start off real easy. So let's say that I give you a part that looks like this, and just assume all the edges are square. And I'll go ahead and number the parts, or number the surfaces for us. Okay. So here we go. Let's say, for example, I want surface, we'll do it real easy. I want surface A, or surface 2, to be parallel to 8. Okay? Take a moment. Think about it. But I want you to control this situation with the feature control frame and the correct use of a geotolerance to guarantee, and we'll just assume for all of our little exercises, the tolerance size is always going to be, well, we'll just make it 2. Okay? Tolerance size for all of our zones and everything is just going to be 2.0. Okay? So whenever you need to put a tolerance size in, just put it in as 2.0. But that's what I want. I want you to put a feature control frame on this drawing that establishes that surface 2 is going to be parallel to surface 8. Do everything that needs to be done to establish this. Questions? All right, hop to it. Yeah, to get started with. There you go. There's your feature control frame and an arrow. Okay, so walk me through this. I need to establish that surface 2 is parallel to surface 8. So what's one of the first things I should probably do to get this set up? Establish the datum, right? We'll go ahead and establish our datum. So we'll do this symbol, right? This is our datum reference, correct? So do you agree that I put it in the right place? Okay. So then, obviously, since that's there, we need to let the feature control frame reflect that we're going to be referencing that one. Okay, so what goes in the middle box here? 2.0. I'll just do 2 because it's small. And what goes right here? The parallelism symbol. So how about that? Good so far? Yep. All right. So awesome. Now let's turn around and do a little bit different one. I want surface 4 to be perpendicular to 7. So go ahead and add that to your sketch now. So walk me through. What's my first step I need to do to make this happen? I need to establish which one's the datum. So which one is the datum? Alright, now I'm going to use this as an opportunity to show you something. On a set of plans, they won't always be nice and neat and show you a datum here. By the way, I have to name this, I can't name this A again, can I? Now I have to name it the next letter down, or whatever letter you choose. But they may not be always nice and neat and give you this perfect understanding of where this datum is. They may do stuff like this. They may have a dimension out here about something, and just ignore that my 2 happen to be written there. And they will attach the datum to the dimension. Okay? Why do they do that? To keep from cluttering up this space, because there may be other dimensions going on. So you may see datum references attached to dimensions, but they still talk about the same surface. You see how this B is still got the little darkened triangle and it's floating right across from this surface? That lets you know that this surface is still that datum, because technically this line is infinite. It doesn't really matter if it's touching the surface or not. It just means anywhere along this theoretical plane is a datum. Y'all see that? Does that work for you?
6 would be the measurement for
It would have been the opposite, yes. Absolutely. If you wanted 6 to be the one, the measurement that they may be using to mark it would be over here, like that. In some sense, yes. You can see it that way too. You'll start to, if you see a set of plans with this, you'll know right offhand what I'm talking about. We'll see if we can get some more examples as we go along, but just be aware that they always won't be nice and neat where they put the symbol right there on the surface. It may be floating off, it may be on a dimension, that kind of thing. I will. In a second. Let's get through this one and then we'll see if we can find some examples. Okay. So first step was to establish that a B datum is establishing that 7 is the controller. So now what do I need to add to 4? Right, feature control frame. I need to put what in this box right here? B. What's my size? 2. And what's my symbol here? Perpendicularity, and we're golden. So straight up, straightforward process. Now let's do another one real quick. Let's say that I want a straightness tolerance on surface 1. Straightness tolerance on surface 1. Go ahead and knock that out. Straightness tolerance on surface 1. Okay, so this one's pretty straightforward. I'll get you started. There's going to be a feature control frame. By the way, feature control frames don't typically, they don't change directions much. A lot of times they will back angle the arrow like I've done here. But this one will only require 2 boxes. Just for reference. Now, what goes in the first box right here?
surface symbol.
Straightness symbol. That one right there. Just one little horizontal line is your geo straightness tolerance. Okay. Now, what goes in the box after it? 2, your size. Now, we don't really have to have a datum associated with this particular choice. It's just straight, okay? So they can sometimes be given a datum, but not always. So you may see it either way. They may relate to a dimension or something of that nature, but for the most part, we could get by with just understanding this thing needs to be straight. It's possible. It's possible. What they would typically do is they would actually link a dimension to it, and B is a possibility. That you kind of see where these things start to overlap, where that could also be established by parallelism, and you'll see different tools used to accomplish the same thing. Now, going back to your previous question, here's an example where they throw the actual feature control, or I'm sorry, the datum symbols, datum reference symbols on the dimensions. If you look right here, notice that B is not actually touching this surface. But it's talking about that surface because it is attached to the dimension describing that surface. Same thing's true with C. Now this one's a tricky one. And this is an important concept to get. So you look at this one and you might be thinking, oh, okay, they are establishing this wall right here as a datum reference C. And that makes sense to think that way. But there's a tricky rule when dealing with cylinders. What they're actually doing, since they have attached this C to the dimension of this cylinder opening, is they're actually establishing the cylinder in itself as being a datum. So technically they are establishing the center line of this hole as the datum. Watch out for that. You know, normally when it's attached to a surface, everything's all hunky-dory. So for example, A down here is attached to this surface, so it's the back of the part. So they're measuring from the back of the part out. They're measuring from this surface out. That'll make sense. And you also see that this one, in fact, may also be a diameter. Even though I said it was the surface, it's actually the center line of this cylinder. So they're tricky sometimes with how these datum symbols are played. So, you know, they may have been going for this surface, but in reality they're probably establishing this cylinder size as a datum and then this cylinder in that case. The easiest way to tell is to look at what they do feature control frame wise. So won't go into that right now. That's a little bit above where we need to be at the moment. Yeah, it blows your mind when you start to see all the complexity of this stuff, but that's okay. We'll get there. We're just worried about the basics. Key thing I want you to see this and take away is that the feature control, or the datum reference doesn't actually have to touch the surface in question to be implying the surface in question. It can be off on a dimension related to that feature. Okay? So when you see that, try to understand that's what they're going for. Let's go back to our work. Okay, so let's turn around and add something else. I want a flatness tolerance applied to surface 7. Flatness tolerance on surface 7. Oh, so I wanted surface 7 to have a flatness tolerance. So here we go. Feature control frame. It's got a box. What's in this box right here? Flatness symbol looks like that. Tolerance size is 2. Now, little side note, sometimes you'll see datum references here for no apparent reason. Flatness tolerance is just really about the surface roughness of something, so to speak, like how much the surface deviates. So likely you're not going to see a datum reference, but it's possible a designer could throw it in there, but not super relevant if they do. Yeah. How would they check it? Well, there's several devices they can get to check surface roughness. Devices include the ability to, let's see, I can't delete this. Yeah, I can for a second. So, get back, yeah. So, we can actually take if it was a cylinder, we can pick a little measuring tool that will give us a readout. And as it spins, it tells us how far the dimension has changed from there to there. There are what we refer to as the CMM systems, which will essentially, measure with a computer control system to tell us what we're getting parameter-wise versus not supposed to get. There's several tools that can check the roughness and those factors. So it's hard to check. You can't manually check it very easily. Yeah. The art of quality control, and it really is an art, is all about figuring out how to set up jigs and tools to check things like this. Now the go-to move is to use a CMM machine to basically check the measurements for you, but a lot of times templates and jigs can be used very, very effectively. So figuring out how to check that is an important part. But it's a little bit beyond the scope of what we're talking about, but somebody's got to figure it out. You won't be able to gauge this with manual tricks. Let's see, get rid of that. So we had flatness, and we had 2. That wasn't a very good symbol for flatness. We had flatness, and we had 2, and there we go. Now let's just throw a little extra into it. Let's go back to drilling some holes. So now our part has a big hole in it, and we're given some, we're given some dimensions. My drawing's getting cluttered, but here's what I want. I want a true position tolerance applied to this circle. This hole. True position applied to this hole. True position. So let me do some erasing real fast. True position, pretty simple on something like this. I will show you one slight alteration though. So they are going to do maybe a feature control frame that does this symbol, does 2, and I'll get to the next thing. So far, do you agree or disagree? Disagree, why? Needs a diameter symbol, doesn't it? Because your zone for true position is typically going to be a round zone. Now, little thing I may add, there may be a datum reference back here on some prints, because what they're going to want to do is establish that yes, this is a true position, but it has to be true position based on something. So there might be a dimension from here to here, and a dimension from here to here, that establishes where the hole is supposed to be to begin with, for you to even check what the true position is supposed to be. And this will typically be associated with the datum. So for example, I could technically reference the datum A and datum B in that situation. Understand why that is? Datum A and datum B are being used to give you the values. Let's say that hole is supposed to be, I don't know, 27 units this way and 16 units this way. So you have to technically know what those dimensions are to be able to check what the true zone is supposed to be. So they're going to maybe add the datum references of saying, okay, you're coming from B down 16, you're coming from A over 27, so you have to use these datum references to even check the actual true position. So you may see a true position on a set of plans that actually has datum references. You also may see a true position that doesn't actually reference the datums because it's just kind of a given. You have to know what the numbers are. So could go either way on that one. Just want to make sure you're aware of that.
Would they ever put both datums in there?
They would probably put, if they're going to put one, they're going to put both of them, because you know a hole has to be located horizontal and vertically from some place. So if they're going to do one, they're going to do both. They may even do three if there was a depth issue where they're afraid the actual hole would be drilled sideways on its way down. So that's a possibility too. Definitely two if they're going to show it though. Questions on this? Alright, so it can be pretty straightforward. Here's what happens though. Look at this drawing. When a person sees a blueprint like this, what's the first mental reaction? What the heck is this? Exactly. Your brain gets overwhelmed when it just sees all these numbers and symbols and things. You're like, what the heck? That's normal. It's okay. The trick to dealing with these type of dimensions and things is just to isolate what you can. First of all, I start with the letter A. I see it down here and I'm establishing, okay, well this makes sense. Look what we're doing. We are using the back side of this part as a datum. Agreed? Does that make sense? And while we're at it, we're going to throw a tolerance on it of, what type of tolerance is that? Flatness. And we're going to give it a zone size. And we're going to say that while we're at it, datum A is also going to have to be pretty smooth within a tolerance of 0.002. So that means if I check the back side of this part all the way up and down, I should see a point, my tolerance zone for flatness is 0.002. And then I move on. Okay, well what things actually matter to A? Well, check it out right over here. Here's a feature control frame that is referencing this edge right here. And it's saying that with reference to datum A, which we just established as the back of the part, we need this surface, or probably this hole, this cylindrical hole, to be perpendicular to that back surface within a zone of 0.005. Now you will notice that they do throw a diameter symbol in there. That can happen because technically a line can wobble, or a center line can wobble out of, all the way around. So that's why they're using a diameter value there. Regardless, whatever it means this. Let me simplify it for you a little bit. Here's a block of material. Let's try that again. Here's a block of material. There's a hole going through it. I'm establishing this surface as datum A. While I'm at it, I'm also establishing that feature control frame says this needs to be flat within 0.002. Okay, we're good so far? And just for the benefit of us doing this, I'm going to make it a section view. So this entire surface from here to here has to be flat within a tolerance of what value? 0.002, right? And this back surface also happens to be what for the overall part? A datum, right? So then this next one comes in and says, all right, we've got this feature control frame, and we're going to say that it's referring to this particular measurement. I don't really like the way they did it, but we'll work with it. Let me expand this just a hair. There we go. We're going to use a perpendicularity. Agreed? You cool with that so far? Perpendicularity? We're going to say the zone is going to be diameter symbol 0.0015. And we're going to say with respect to datum A. So what are we trying to control? We're trying to control that this hole is perpendicular, or the center line of this hole is perpendicular to the back side of this surface. That's what we're trying to control. But how much? Well, our theoretical perfect zone, our tolerance zone, is going to be 0.0015 wide. And it's going to be three-dimensional. So it's basically round, and the round goes in and out of the page at us. Okay? Because technically this center line could wobble. It could be going this way, it could be going this way, it could be going into the page, out of the page, that sort of thing. That's why they have a diameter value there. Didn't necessarily mean they had to, but they did. Okay? Do you understand that? Do we have questions on that stage of it right now? Okay. So then you use that logic to keep on going through the rest of the part. Look for example, they have parallelism. So are we pretty good with parallelism at this point in time? Yeah. There's surface, we're referencing surface A. This surface needs to be parallel to surface A within a zone of that big. And so there we go is kind of the process. But yes, your brain has a tendency to get overwhelmed. So the solution for dealing with these things is take it just one little detail at a time, focusing in and ignoring everything else for the moment. Question?
And it's a good way. And like you say, you're starting with A. Now, is whoever made the blueprint,
yep,
are they trying to stay on that basis too?
The objective of any designer, engineer, whatever the case may be, is to make the blueprints readable and minimize potential mistakes. Because the more mistakes are made, the more the cost goes up. So it is their job to create a set of plans that make sense. However, you know, the workplace is full of responsibilities and tasks. It doesn't mean that somebody may have to send a plan out that's not that great in terms of layout. Yes, possibly. So it's just everybody's trying to give a good print, but it doesn't always mean that they're going to follow the same procedure. As far as kind of guidelines, yes, this is the best format. Choose the thing that is the most dominant of a datum feature and call it A, and then move on from there. Other questions? All right, it's a good stopping point.